Welcome back, guys. I don't know if anyone has clicked the link for the slides yet. Has anyone done it?
Just feel free to let us know once you're on the slides.
And the attendance code today is New York. That's still also the thing that's still going on. If you're looking at all the attendance codes, has anyone like guessed the pattern to them yet?
It's not obvious, I will say that.
It's really not obvious.
But if for some reason you know what the order is,
Yeah.
I think did you say it's not hard?
It's not obvious.
Okay.
It's very hard. I think it'd be useful to give a hint at this point. All of these attendance codes are like, if you take them together, it's a ranking. Like these cities are a ranking of some sort.
Like based off of like a metric?
Some metric. Yes.
Okay.
And I'll send the past attendance codes in the chat.
Yeah.
So is everyone on the slides? Because no one's saying anything in the chat.
Guess no one's.
We should paste the link in the chat, I guess.
Sorry. This was a genuine mistake yesterday. And that would be funny to keep it in. But here's the real slides this time. Oops. It's in the chat. So it's the same thing, except you add dash for real this time. But yeah, we made a mistake and accidentally like made a tiny URL link to like Google Images dosas. We fixed it.
What a dosa was, and that ended up in our slides. Also, while you guys are getting on the slides, for context, the YouTube video is, I think it's called Rickrolling when you send that video to someone, and it's kind of like a gotcha thing if you get someone to click it. It's not just a random video.
Yeah. All right. Since it's in chat now, I think I'm gonna just move on to the actual workshop. I won't take any more of your guys' time. But yeah, so first off, we're gonna start off with like a quick review of logistic regression, actually show a little quick demo. And then we're gonna go into multi-class classification. Oh, you need edit access. Is it still not letting you see it?
Yeah, for the slides.
Okay, let me fix that real quick. Anyone with the link? Okay, you should be able to view it now. Yeah, so we're gonna go a quick review of logistic regression, and then we're gonna go straight into multi-class classification, which is just kind of be like a small modification to logistic regression that we learned last week. Just the same way that like logistic regression was a small change to linear regression from the week before. Yeah, so this is a demo. If you click on the link, you'll get to a page that looks like this. It's written by the team that makes TensorFlow. It's a popular machine learning library or framework. And this is really for neural networks, but we can actually turn this into logistic regression by just reducing the number of hidden layers to 0. So it's just like a single, it's like a single node. And then you can change the activation function to the one we learned, which is sigmoid. Well, it doesn't really matter in this case. You'll see that there's some other options on this page that you can play around with, and I highly encourage you guys to like play around with it. There's stuff like the learning rate and that we've also seen before when we were talking about gradient descent. This is how fast it, or how big each step of gradient descent is. Regularization, we didn't really talk about at this point. We may talk about it more when we, definitely in advanced track, and maybe a little bit when we get into the actual guided project. But for now, you can just set it to none since it doesn't really matter. You can also check or change between classification and regression type problems. But for now, I'm just going to look at classification because we just went over logistic regression. What's interesting here is that, so here on the left side, you can select what kind of data set you want to be like classifying. So we can just start off with something simple, right? There's two different clusters on the side. In this case, we have two variables, x1 and x2. So this x1 is represented by this axis on the bottom, and x2 is represented by this axis on the top. And you can see that they range between -1 and 1. And so like if I hover over x1, you can kind of see on the right side that it's like over on the left side, it's like a negative value, and over on the right, it's a positive value. And the same goes for x2. Or sorry, that's not the range of x1 and x2. The range of x1 and x2 is like -6 to +6. But the category that's in, the category of each point is represented by the color, -1 or 1. With sigmoid, we had it to be like 0 or 1, but you can kind of just, you can change it to something like tanh, and then that would be mapped to -1 and 1. But if we just do this, start off something like this, and then we start training, you can see that that was really quick, but slow down the learning rate a little bit so we can see that. You can kind of see that's a little too slow, but let's see. Yeah, there you go. You kind of see how it kind of, every gradient descent, you can see how it learns the decision boundary between these two groups of points. And that's sort of what we've been looking at, binary classification. But if you select a different kind of data set, like this one, where it's not linearly separable, you can see that no matter how long we learn for, or if even we set this learning rate to something more reasonable and then we start it, it's not going to be able to separate these two groups of points, the yellow ones from the blue ones, because the only data it has is, or the only information it has is these two variables. And using these two variables, there's no way you can draw a line that separates these two groups of points. And so no matter how long you train it, it's not going to be able to separate it with the model that we have. You can try other ones as well, like something like this. Again, same problem. And something like this, that's definitely not going to be able to do it. But this one, it can separate the two quite easily. But you can notice that there's other things, other features that we can select here. So this is x1 squared, and this is x2 squared. So if we stop this, reset it, if we add in these two features, x1 squared and x2 squared, in addition to our two original features, you can see that it separates the data, and the boundary is not kind of linear anymore. It's still a linear classifier, but it's only able to do this because it has some more information. So it's linear when in these 4 axes, but since it's projected into these 2 axes, then it looks nonlinear. But you can see that now that we added these 2 features to it, it can actually separate this nonlinear, or nonlinear when you only have these 2 variables. But when you add x1 squared and x2 squared as a feature, then it is linearly separable in this space like this. So even without neural networks, you can still model, or you can still like separate data that might look nonlinear on the surface like this. And you kind of try to see how it does on other stuff. Like this one, it definitely fails on. It's not able to separate this. This one, there's no way. And yeah, we can also take a look at regression. Turn off these training. So it's not a line in the same way, but like these are the 2 axes, and it's very similar. I didn't really want to show this that much because it's not very easy to see what's going on with regression, but classification, I think, is a lot better, or a lot easier to see kind of how it's learning this decision boundary. Right. So you guys can kind of play with this later if you want. We maybe explore it, or if you have any questions about it, you can play around with it. Yeah, I just wanted to share that because I think it's a useful way to visualize what we've been doing up until now. So, logistic regression. Let's review a few of the concepts that we learned last week. The first one is the sigmoid function. Can anyone tell me sort of what is the purpose of this function? Like, why do we even look at this or consider this or add this to our linear model? You can either unmute or like say it in chat, kind of discuss it.
Yeah, the main purpose is we want to take like a infinite input of numbers and kind of squeeze them into like a finite range. And then I guess it's helpful for classification because you can just pick like an arbitrary spot between 0 and 1 and say like below this it's class A and then above it it's class B.
Yeah, that's exactly right. Thanks for the answer and thanks for participating. So yeah, we could choose an arbitrary threshold, for example, 0.5, and then if it's below that, then we can classify that as class 0, and above that, classified as class 1. Yeah, and then it neatly divides the like all real numbers into less than 0.5 and above 0.5 right at 0 here. So with logistic regression, what we took is our linear model, which is our weight vector multiplied by our feature vector, and added a bias to it, and then apply the sigmoid function. And our inputs are going to be classified as either 0 or 1. And essentially what we're doing is we're kind of learning that decision boundary that we saw in the demo between these two different classes. And like I said, this is binary classification because we're binning all of our samples into either one class or the other class. So now let's take a look at the class function for logistic regression. In contrast to linear regression, it was binary cross entropy. For logistic regression, it's binary cross entropy, and this is the formula for it. Y hat is the prediction, and Y is the label. Now, I want to ask for your guys' participation since this is review again. What do you guys think happens when Y is 1? What does this formula kind of simplify to? Yeah, either in chat or unmute, whatever is more comfortable for you guys. So like, if you substitute in Y into this formula, what does it simplify to? Someone says negative log Y hat, and that's exactly right. When you substitute Y into this equation, this second term turns into 0, so this term cancels out, and we're left with only this one on the right here. And you can see that if Y is 1 and when Y hat is higher, then when Y hat is closer to 1, then we get a value closer to 0, so it's small. If we have Y hat close to 0, then we have a large negative number, which it gets inverted by this negative sign in front, and so we have a large loss. And can anyone tell me what happens when we do when Y is 0? When our label is 0, essentially. What does it simplify to? In chat or unmute.
Negative log of 1 minus, Y hat.
Yeah, perfect. Thanks for answering, and thanks for the people who answered in chat as well. It's exactly right. It's only that's the second term, since when this is 0, this cancels out. And it's the same idea. So if Y, it's the opposite of the first one. If Y is close to 1, then this whole expression is close to 0. And if it's close to 0, then it's a large negative number that gets inverted. So it's a large positive number. That's our loss. If it's close to 1, then if it's close to 0, then it's close to 1. And if it's close to 1, then it's close to, then log of that is close to 0. And negative log of that is still close to 0. So you have a small loss. Right. For a quick poll, what task is logistic regression well suited for? Is it A, B, C, or D? In chat, or if you want to unmute. And maybe if you unmute or in chat, you can kind of like explain why you think it's B. Okay, someone in chat says it's B. Anyone want to explain why B might be the right answer? Any ideas? You can just throw out ideas. Someone else says B or D. Okay. Anyone have any ideas why, or any logic for these choices? Why would logistic regression work well for B? Let's just look at that one first. Is it classification between two options? That's exactly right. In B, we have two different options. We have predicting whether to approve alone or deny alone. So it's binary classification. Facial recognition software is also a good choice, but it's not exactly right for logistic regression because you could have like facial recognition software where you're just trying to differentiate between two different faces, or whether or not it's a face at all. You could kind of, I guess you could use logistic regression for it, but I expect it wouldn't perform very well. It's a very simple model, so I'd expect it underfit, and yeah, it wouldn't really perform well. But it is possible. So I think either B or D would work. B is probably the best answer, but I could see how D would work as well. Yeah, so let's move on and talk about multi-class classification. First, let's talk about, oops, where mouse go? Our labels. Imagine we had the task where instead of we're just trying to bin each of our data points into one of two classes, that we have multiple classes, hence multi-class classification, right? We have photos of cats, dogs, chickens, and fish. So there's 4 different types of categories that we have in this case, and we want to classify them. How can we kind of assign them, or yeah, we kind of want to assign them a value, right? Does anyone have any suggestions for how we can assign them a value? Will we just do it maybe arbitrarily? Any ideas?
I guess my first thought is to do multiple, like single step classifications. Like the first one could be, is this image a cat or not? And then if it's not, you could like go down the line, and then you can like ask another question.
Yeah, that's a great answer. And that's actually the conclusion we'll be coming to. But in this case, what we're gonna try, one way you might think of doing it is just assigning each of these classes a number. And you can do it like the cat is has the class 0, the dog has class 1, the chicken has class 2, and then the fish has class 3. If we of course have another category like dog, then we wouldn't have a class for it. But suppose we just had these 4 categories. Does anyone see a problem with doing it this way? Like if we assign, so suppose we assign each of these a label, like a number between 0 and 3. And we trained maybe something like linear regression to choose one of these numbers. Do you kind of see a problem with doing it that way? Like what kind of implicit assumption are we making that's problematic here by assigning? Okay, yeah.
Isn't the big issue that like if you assign those values, you would assume like cats and dogs are the like most closely related versus like chickens and fish should be more closely related, like
Yeah,
just by nature of like, yeah.
that's exactly right. Yeah, thanks for the answer. I really appreciate it. Yeah, so oh yeah, sorry. This is a dog, so this would be class 1. But um, the problem with that is that we're kind of, because they're on a scale between 0 and 3, that's kind of implying that a chicken is as close to a fish as a chicken is to a dog, and a cat is more different from a fish because the difference between 0 and 3 is larger than it is from, say, like a chicken, which is 0 and 2, which could be true, but it's not necessarily what we want to do. We want to classify each of these classes independently. And that's what we're going to do when we use a one-hot encoding. There's another reason for it that we'll kind of see when we look into how we change our model to kind of handle one-hot encodings. But until that point, I just want to introduce the concept of one-hot encoding. So what we do with a one-hot encoding is that for each of these images, we're going to be assigning it a 0 or a 1, but in a vector like this. So a vector is going to have the same number of, or it's going to have the number of dimensions or number of scalars as you have categories. So in this case, we have 4 different categories. So we have 4 different values in our vector. And we assign it a 1 if it's this category and a 0 otherwise. And essentially, this is a one-hot encoding. And this is also assuming that each of these images only fits in one of the categories. So if you had like an image of a cat and a dog in the same picture, we wouldn't label it as a cat and a dog. Well, we wouldn't be able to do it this way because of the activation function that we're going to use at the end. But before we get to that point, yeah, I just wanted to mention that it is possible to label it, like, you can put a 1 as a cat and 1 as a dog if you have a picture of a cat and a dog, but it's not going to work for our purposes here. So that's why it's a one-hot encoding. We're only selecting one of the categories. And then we can do the same thing for all the other categories. So the cat is in the first position, the dog is in the second, chicken is in the third, and fish is in the fourth. So now we're going to talk about how we're going to change the output of our model. I want to first talk about, or go back to how we had our logistic regression model, or how our model for logistic regression looked like. We had 3 different components to it. The first one is our features, our feature vector X, and then we had our weight vector W and our bias B. Can anyone kind of tell me, like, what role does each of these vectors kind of play in our model? Or maybe another question, maybe more specific, could be like, what are we training in our model? What are we learning?
Yeah, I guess the features are like the input data that we have attached to like an actual Y value that we're trying to achieve. And then the weights, I guess, are the like how important each feature is in the sense of like which ones we want to weight more for our model. And then the bias is like, I guess, the minimum threshold you need to I guess, activate or classify something as such.
Yeah, that's a great answer. Thanks. And that's another great interpretation of the bias. It's a way of adjusting where your threshold is, that 50% threshold, if you set it to that. But yeah, that's sort of the purpose of this. And one drawback to this model is that the output, because we're multiplying, or we're taking the dot product of our weight vector and our feature vector and then adding a scalar bias, is that the output is a scalar. Right? And if we had a model, or if we used an encoding scheme like the one that we first talked about, where we assign a different number like 0, 1, 2, or 3 for each of the categories, then we could use something like this if we, of course, didn't pass it through like a sigmoid function. But we decided to use a one-hot encoding, and so our labels are actually a vector. And this model only outputs a single scalar. So how can we modify this so that we output a vector instead of a scalar? And this time I kind of want someone else to answer if that's possible, either in chat or out loud. Any suggestions for how would we take, we've taken, a tried and true formula, taking our weight vector, multiplying it by our feature vector. Oh yes, someone else answered. That's exactly what I was looking for. Using a matrix. Thanks for the answer in chat. So what we're gonna do is we're gonna take our feature vector, but because we wanna output a vector and not a single scalar, we're instead going to multiply it by a matrix. Our weight matrix is going to, or our weights are not gonna be a single vector, but it's gonna be a matrix in this case. So it can be an n by c matrix where n is the number of class, or n is the number of features and c is the number of classes. And when we multiply that by our input vector, then we get a output, and we get an output that we add to our bias vector that's the same dimension as the labels that we had before. You might notice that it's n by c, and our input is n by 1. So you'd actually have to take the transpose of our weight vector, but we'll see that in a bit. So let's take a look at one of our examples here. Oops, sorry. The first step is to take our pixel values from our picture. So we're classifying the images of cats, dogs, fish, and chickens. So the first step would be just to take our image, convert that into a vector, right? And this vector will represent each of the pixel values in the image. The next step would be to multiply that by our weight matrix. And because our weight matrix by convention was n by c, so we want to take the transpose of that so that it's the output is going to be 4 by 1, which is going to be what we add to our bias and finally come out to our prediction z. Does this process kind of make sense? So essentially what we're doing is that each of these rows in our vector is like one of the logistic models that we had in the past, but we're kind of stacking them together by using a matrix as our weights instead. So yeah, in this case, each of these rows would correspond to one of the weight vectors, or each of these columns would correspond to one of the weight vectors in logistic regression before. And essentially we have like a different logistic regression model for each of the classes that we have. But now this poses a bit of a different problem that we'll be talking about in a bit. But before that, let's do a quick poll to make sure you guys understand. If we have F features, C classes, and M training samples for X, what will the dimensions of our weight matrix be? Is it A, B, C, or D? I know it was just like in the previous slide, but if you guys can answer, that'd be great. Just to kind of drive home the point. B, someone says. And that is correct, right? By convention, we're going to put the features first, and then the classes as the second dimension, number of classes as the second dimension. And then when we multiply by our input vector, then we take the transpose of that. But yeah, now I'm going to hand it off to Nikhil to talk about Softmax. And this is going to solve the problem that I kind of hinted at earlier.
All right, I'll share screen right now. we'll talk about softmax. Okay, you guys all see this? Yep, I hope so. All right, I just want to go back to the slide that Ben was talking about just before to actually point out the actual issue he's talking about. I think it's really clear here in particular. So we had our pixel values from our cat. We turned them into a big long vector. We flattened them, like Ben said. And we took that vector and multiplied it by our weight matrix transpose. So like the transpose of the flip. And then we add our biases. And we get our n vector, which has four elements for 4 classes, right? But one important thing, actually, I want to ask you guys what the important thing I might be noticing here, and Ben pointed out earlier, is like, what do you guys notice here in these numbers in these classes, and like what could be problematic about, I guess, like these numbers in particular, relative to each other, that could be a problem for our algorithm. Also, this is kind of a general question, so feel free to throw in guesses or anything you guys are thinking about. But yeah, also I can't see chat anymore, which kind of sucks. But actually, I can. Never mind. I'm bad at looking at that. But all right. Yeah. What do you guys think is the problem? Any guesses about why this vector right here on the right is kind of problematic for our classification? It can be a guess too. It's not to be like a concrete answer. It's a hard question to answer, actually. So anything is fine. Feel free to answer. Oh, sorry, go ahead.
I guess it's because we have to like simplify it to one of the like 4 classifications where there's just one value equal to 1, but like that wouldn't take into account the relative magnitude of each. I don't know.
Yep, exactly, Austin. Totally right about that. The important part here is like how you look at like 23 compared to 1, and that's a huge magnitude difference. It's like, for example, I'm sure we've all looked at data before, and we looked at like, I don't know, like comparing like how much how much you weighed to like how much your dog weighs. Actually, that's not a good example. What's a small animal? How much a hamster weighs? So like, let's say your hamster, like a bunch of hamsters, you take a bunch of hamsters overall, and on average their weight is like 5. Oh, that's a lot for a hamster, like 2 pounds. Might be a little too low. And the standard deviation is like a pound, right? While for humans, like this, the average is like 79. Oh, that's really low. I would say 112, 20 pounds. And like the standard deviation could be like 20 pounds, right? And so if you're comparing directly like that 120 average to the 2 pound average, you compare it directly, you're going to have some problems, right? So we usually normalize your data over given the standard deviation and all to make sure that we can actually accurately compare those. And so it's kind of what we're doing here with our activation function that Ben hinted at. We're basically making these two all these different classes kind of comparable. And as Austin said in his comment, making the magnitude kind of similar so that we can actually compare them. And so that is the magic of softmax. And so we're going to get into softmax right now. And so softmax is a really nifty activation function that's pretty simple. So now our output vector is 3, 4, 1, 2. It's a 4x1 vector. And so now what we want to do is we want to make it like all be between 0 and 1. And so what we do is we take the sum of all, for each of these, we take the sum of e to the power of that. So e to the power of 3, e to the power of 4, e to the first, and e to the second. And you get that sum. And then for each element, we take e to that power and then divide it by the sum. And so what that ends up being here for the first element, it's e to the third over the sum of all 4. And the second element is e to the fourth over the sum of all the e's powers. Same for 1, same for 2. And so what you'll notice here is that because this is like a single value over all the values, is that these actually add up to 1. And so that's really nice for us because probabilities all add up to 1. And so now we have like a probability spread for each of the 4 classes that we can use to determine which class we think our data point most likely is. And so a question I have for you right now is that why do we have this really kind of complicated looking function right here? Why do we have an e to the z and like a summation of e to the z? Like, why can't we just take a ratio of like 3 to 4 to 1, or 3 to the sum of these things, and like 4 to the sum of these things. Like, why do we have this complicated softmax function instead?
Yeah, I was gonna ask you the same thing too, because it seems easier if we could just do like 3 over the entire sum. But I guess it gives more weighting between the difference between like numbers that are farther from 0. Like the difference between 3 and 4 is a lot greater than 2 and 1, which is good to take into account because those are like the extreme values.
Mm-hmm. Yeah, actually, the like I guess the yeah, if it's really big in that case, like if this value on the left is like, I don't know, like 1 million or something, and like everything else stays the same, you get like e to the 1 million over e to the 1 million plus e to the fourth plus e to the first plus e to the second, and those terms don't really matter anymore because what's e to the fourth compared to e to like a million, right? You said so. In that case, this value would be really close to 1, but it's actually good for us because that means that we're probably confident in our in our classification. I guess the main reason why you'd actually want to have not have a ratio is because of the thing we mentioned right here of not think about negatives. And so if you have like the sum of all of these, and you took like 3 over what's that, 3 plus 3 over 10, and then 4 over 10, and then 1 over 10, and then 2 over 10 as our percentages. It might not work the same for negative numbers first off, because you have like a negative 3. This turns into a sum of like, it's like negative 3 over I can't over 4, and that's like weird. And then you get like 4 over 4 is like 100%, or stuff like that kind of messes up. And so you could have problems with negative numbers first off. And also, as we'll go into later, this function is actually really nice for its derivatives and how it comes in for taking the gradient descent. And so if you guys all know e to the z, the derivative of e to the z is e to the z. Really convenient. And so we'll get into exactly why it's convenient for looking at gradient descent. But now just remember that softmax takes our unnormalized, you can think of it, output data and turns it into like basically probabilities of likelihood for each class. And so quick recap again. So if we have C classes, basically take that each of those classes, each of those values in the vector, take them to the raise them to the raise e to those values. Then we multiply that by the sum of all the vectors in this original vector. So or sum of all the values in this vector. So we take e to the 1 or e to the z1, e to the z2, e to the z3, all the way to e to the zc, a sub c. We take that sum and divide it, take the reciprocal of that and multiply it by this. And so we're going to get a bunch of ratios basically. So we're going to have a bunch of A's, which are our final result, and those all will sum to 1, which is really useful. So from start to finish, we have a bunch of big, maybe like unnormalized, like really different values, and we turn it into a bunch of probabilities. Any questions about that?
Is the derivative thing like the main reason why we use base e versus like other numbers?
Yeah, I would think so. Ben and Vaishnavi, you want to add in too? I mean, I know like 2 to the power or whatever, but you have like the ln part too, so that's more complication. So I would think that's probably the main reason you go e, because derivative of e is just e. So yeah. All right, yeah. So I'm just gonna, yeah, I think that's probably the most reasonable option, because it's just like, it'll come into, you'll see it more when we look at gradient descent and see how easy it is to take gradient descent in this case. But e to the z is a really useful function in general. So yeah, we have our softmax, and so now we need to first figure out our cost function as well, because we need to figure out how bad our model is and make it better. And so last week we looked at binary cross entropy, and that was between either one class or like another class. There's only 2 classes off, only 2 options, so it's binary. Now we have like a big, not two, we could have like 5 or 6 classes. And so we're gonna get rid of the binary stuff. Let's go look at cross entropy. And so before we had only 2 classes to classify between. So like, is it gonna rain or is it not gonna rain? Or like, am I gonna fail my midterm or am I gonna not fail my midterm? That kind of thing. And so now we need to go switch that mindset to, is it like not just 2, but actually like any number of classes. And so it could be, is it a cat? Is it a dog? Is it a fish? Or is it like something else? And so we need a general loss function for that because our binary cross entropy doesn't quite apply again to this case. And so as normal, when our model makes a bad prediction, so when our model is really off on its prediction, so like if it looks at like a dog and it says it's a fish, that's pretty bad, right? And let's say it actually turns out to be like our model, like our n vector is really off. We need to make sure that our model knows that that's really bad and have like a high cost, so it's a really bad value. And so yeah, quick explanation. So if our probability for like a certain class is really far away from 1, so let's say we gave it a dog, which is like has a 1 in like the dog class, and it turns out for our end result we have like a 0 in the dog class. That's like a big alarm for us because it should be 1, it's a 0, so it's kind of like polar opposites right there. And so that should have a high cost. And then, so putting that all together, we have a function that's really convenient called cross entropy, also called categorical cross entropy because categories for classes. And that's really helpful for both of these and sets up both of these conditions. And so looking at cross entropy, you also see that's pretty similar to binary cross entropy. It's actually basically the first term of binary cross entropy. So it's pretty similar. An important distinction that you'll see is that, let's say our label is like a 1-hot encoding. So 0, 1 means this is the correct class, and then 0, 0. Then our output's going to be a bunch of probabilities. So 0.18, 0.27, 0.54, 0.01. And so looking at this right here, what we're going to see is that only the class that has the 1 in the label, so the second class right here, is going to actually contribute. So you can see that by plugging in these values right here. So you take the sum over C, in this case, C is 4 because we have 4 classes. And so from I equals 1 to 4 of y sub I, so our first label times negative times that times the log of this. But what's negative of 0? 0. So we're not going to even care about this term. Then we get to this term. So we have second term is I equals 2. This weird pop-up. Oh, whoops. Okay. But yeah, second term, negative 1. So y2 is y2 right here, negative 1 times the log of this value. So that point actually counts. So when I equals 2 and we get to the second element or second row of this vector, that value actually contributes to the cost. And then as we'll see for I equals 3, you have y3 is 0. So that gets canceled out too. So this row doesn't matter at all. And then y equals 4. Same thing, y4 is 0. So we're not going to actually care about this row as well. So the really important thing is that only the class that's actually being seen here, so the 1-hot encoding has a 1 in that row, actually gets counted towards the loss. And so as a result, in order to minimize that cost, we need to get this prediction value for that class as close to 1 as possible. And so that's what we're trying to do at cost entropy. Any questions about that or how it works?
Is the reason why we kind of ignore the other values is because I guess their values dependent on the entire activation function, like all their values are kind of inherently tied together. So like if the 1 is pretty off, it should be a pretty clear indication that the entire thing is off.
Yeah, that, and also one thing that I was thinking about when making this slide is that let's say let's think about it as like you have like a picture of a dog, right? You don't want your picture of a dog to train the weights that help contribute to like this is a fish, right? The dog class doesn't actually give you anything about what a fish looks like. It tells you what a dog looks like, right? And so if you're correcting the fish prediction based on you see a dog, doesn't really make sense, right?
Yeah.
So on that note, you probably want to only focus on the actual class, because these other classes aren't really directly linked to the input data you just saw.
Gotcha. That makes sense.
All right, great question. That was a great question. Any other questions? All right, I'll move on. If you have any other questions, just feel free to ask. Yeah. And so, yeah, so just doing that over all of our samples. And so this is for exactly only one training data point. So this is one label, or no, one prediction and one label. Now we're doing it over M labels. And so we're doing it, we're taking the loss of our jth prediction and our jth label for our M data points, or for our M pictures. And basically we're just averaging the loss over all of these pictures. And if you actually expand this for our past definition of the loss function, we get this summation down here. We just plug in loss right here, and we get this. Yeah. And so you can see that this yi turned into a yji, because now it's not just here. It's just saying like we're looking at the ith row of this vector. Now we're saying look at the jth data point, or the j number data point in our database, and then now look at the ith row of that. So it's 2 indexes right there. And so just plugging that in, we get to this loss function. That's a function of both our weights and our biases, because our cost function is always a function of our weights and biases. And that's because our prediction actually depends, like as Ben said, our prediction depends on the weights and biases. And so this is why this is a function of weights and the weights and the biases. It's pretty similar to last week, just a bit of a change with our loss function. All right, and so now we can move into gradient descent, because that's our favorite thing to do with models. Actually, though, it's because we need to figure out how to optimize our model. And so it turns out that actually, because of our choice of softmax being e to the z over the summation of all the e to the z's, and our choice of cross entropy loss, that these derivatives, or partial derivatives in this case, turn out to be exactly the same. I'm not going to go into the exact details of rederiving it, but it's 2 parts. Basically, as we talked about earlier, taking the derivative of softmax is just this thing itself. So e to the derivative of e to the z is e to the z. So that helps out with this. And then our cost function, which is cross entropy, is actually just like a more generalized case of our binary cross entropy. As we saw before, it's basically only the first term, of our cross entropy, our binary cross entropy function. And so that means that we can keep these the same. And if you guys want to check this yourselves, feel free to, because that's actually pretty important. So if you guys want to, feel free to go through this function and take the derivative, partial derivative for both. Actually, maybe we'll walk through it maybe later. I don't think I have a whiteboard, but maybe I'll post that later on after the workshop's over, or a couple of days from now. But it's a good exercise to go through and kind of prove to yourself why these are how they are, because it's actually really convenient that we have the same derivatives or same partials as we did beforehand. And so yeah, it's a generalization of our sigmoid function is softmax, and our generalization of log loss or binary cross entropy is our cross entropy loss. And so that boils down to our partials being the same, and basically our weight update equations on the right side are basically the same because our partials are the same. Cool. And so now we can put it all together. So we have our cat. Our cat class is the first class, so we're putting our one hot encoding at the very top. This is, let's say this is like a by C dimension picture. And so what we're going to do is we initially have like an A by B matrix, and we're going to flatten that down into an n by 1 vector. So it's an A times B is n. And so we're flattening these many rows of pixels into one big long row of pixels. Then we can run our linear model. So that's like what Ben talked about, which is multiply this by our weights matrix transposed. A transpose is basically flipping the matrix by like one of the axes, and so that helps you get the dimensions right. And so now we have our output, and we add bias, obviously. So our outputs is now like this. So our outputs right now aren't normalized, and so we apply softmax to them to get a probability. And so now instead of dealing with random numbers like 3, 4, 1, and 2, which you don't really understand, we have probabilities, which makes sense to us. And so this is again a C by 1 vector, so it's number of classes by 1. So yeah. And then you can apply a cross entropy loss function, which takes this vector and compares it to the label, and then evaluates, and we get our loss is 2.4 in this case, for example. And so from that, we can update our model to update the weights with the equations we had in the last slide to make our model even better for the next time. And so quick poll to check understanding. Oh, actually, first, even quicker poll. What's the dimension of the weight matrix in this case? And so right here we have a linear model, and so we're plugging in n features, and we're getting out a C by 1 vector. And so before we go to our quick poll, we're doing our quicker poll, and we want to ask you. I want to ask you guys, what's the dimension of the weight matrix here? And if you don't remember off the top of your head, you can think of it as matrix multiplication. So what times n by 1 equals a C by 1? Yeah. Yeah, okay. Austin says that n by C. And yeah, that is correct. And going into exactly why that is because you might think like an n by C times a C by n by 1 doesn't make sense, right? Because if you remember matrix multiplication, the inner, like, so if you do like a n by C times C by n, the C and n don't match up because they're on the inner. But remember that we're transposing our weight matrix when we multiply it. So instead of an n by C, when it gets multiplied, it's actually a C by n by the transpose. And so we have a C by n times an n by 1. And then by one of the rules of matrix multiplication, our result will be the outer two dimensions. And so if we do a C by n times an n by 1, we get a C by 1. Yeah, it's kind of hard to explain with your hands, but hopefully that makes sense to you guys. If it doesn't, just feel free to ask a question about that, and I can like write it out or go into more detail. But yeah, our base matrix is an n by C, and we're transposing it to make it a C by n, and multiplying it by this input to get a C by 1 vector output. Yeah, and Vaishnavi just put it in the chat, so that hopefully makes sense to people. And if not, we can go into it a bit more.
Quick question. I forgot with matrix multiplication, it matters what order you multiply them, right?
Yeah. And so if you guys look in the chat, Vaishnavi put it in the chat. So basically, you see how like there's a C by n times an n by 1. So the second and third numbers must match up. So n and n must match up for it to be possible. And then the outer dimensions, the C and the 1, are going to be the dimensions of our resulting matrix. And so in this case, n and n match up, and C and 1 will be the resulting matrix size, which is a vector in this case because it's a 1. But that's why it'd be. And if you want to go to matrix multiplication in general, I can go over it like probably after, because we have a better slide on that than I guess beforehand. So that cool with you, Austin? I can go into it like after you finish the slide, I guess. Yeah. All right. Any other questions about this slide in general or the whole process? All right. So now it's our actual quick poll, not a quicker poll. And so our model has five classes I can count. And so we just distribute, we return the following output of 0.3, 0.2, 0.3, 0.1, x for our 5 classes. And we want to ask you guys, what is x in this case, given these previous 4 values? Feel free to unmute or answer in chat.
Should it be D?
Yeah, it should be.
Yeah. So
wanna
the
go- oh,
probability,
Go ahead, go
the
ahead.
probability function or like the vector should add up to 1 because the probability of like everything happening should like be 100%, which is 1. So you just do 0.3 plus 0.2 plus 0.3 plus 0.1 is 0.9, and then 1 minus 0.9 is 0.1.
Yeah, thanks, Trevor. That was great. Does that make sense to everyone? That's like basically what it is. Yeah, so the sum is 1, like Trevor said, and so if these all add to 1, it's a quick algebra equation of 0.3 plus 0.2 plus 0.3 plus 0.1 plus x is equal to 1. And so we can isolate x on one side, like Trevor said, and we get x is equal to d 0.1 set value. And so the important takeaway here is that these all in our final probability output, these all kind of add to 1. So that's how you can figure out what the other output is. And also a cool thing about this problem in particular is that the first and third class actually tie for 0.3, which is kind of cool. So your model will have to figure out which one to actually output, which is a kind of a different thing in itself. It's a kind of cool problem to think about. Like, which one would you choose in this case? But yeah, that's all we got for our multi-class classification workshop. Hopefully that makes sense to you guys. If you have any questions, feel free to ask. But yeah, if you guys can, please fill out the feedback form. The link is, yeah, here, W21 btrack 5 for real this time. Next week, we're covering NumPy and pandas. If you guys don't know what that is, don't worry, we'll go into it. Pandas aren't actually pandas like real life, but they're pretty cool themselves. The actual event code is New York, and Facebook and GitHub. GitHub doesn't really apply in this case, but we'll get into GitHub later on. But yeah, thank you guys. And if you guys have any questions, feel free to ask. And Austin, I'll get into your questions later. Which clarification? Is it the pandas clarification? Yeah, thank you guys for coming. And yeah, we'll see you next week.
Thank you.
Yep. Thanks, Trevor. All right, I'll go back to the slide, Austin, to answer your question. Which slide was it? The slide that Ben was covering. Yeah, okay, here. So your question was about matrix multiplication, right? And how it exactly works, or is something else?
Oh, it was just, I guess it's been some time since I did matrix multiplication, but I was just curious if the order mattered. But
Oh yeah,
I think it does.
Yeah, I'll go into that right now. Actually, it's really important about order. Actually, so order does matter. A quick rule of thumb you can think about is that I talked about a bit earlier. Is that the inner values, so like the second and third values of the dimensions for the two vectors must match up. So px and then px in this case, for it to be possible. And so you could think if you reverse this in the opposite order and you did the x times wt, you get px by 1 times 4 by px, and then 1 and 4 don't match up, right? And so you can't have that output. But the better explanation for like actually why it works is that matrix multiplication, how it works is that you basically multiply this whole row by this column. And so
like a linear combination.
Yeah, linear combination. So like 8 times 3, 32 times 2, 54, 99 times 11, 10. Actually, this case, this is a transpose of that. So but yeah, it's really important that number of elements this way matches up number of elements this way, like down, so that you can actually multiply it out, because it's like you had 4 elements right here and 5 elements down here, right? You don't have enough for the linear combination, right?
Yeah.
And so the order matters for that reason, because like 8 times 3, like this has more than 4 elements and this has only 4 elements. But if you transpose it and do like whatever the transpose of it is times this, you get that. So I guess a quick example would be like, so let's say this is actually like this example right here. This is only 4 elements right here. Like 3, 2, 4, 11, 19 is that vector. You have 8 times 3 plus 32 times 254 plus 99 times 11 plus 10 times 19 equals the first element of your output. And then 13 times 3, that yada turns into the second element of your output. And then third row and that, and then onwards you get the whole first column. And the same applies if you have a bigger, if your second matrix, second thing is not a vector but a matrix.
Oh wait, but that's transposed, right?
In this case, it's transposed, yeah. But the same way of multiplying matrices works if both of these aren't like both of these are matrices. So like, you know how we did like 8 times 3 times plus 32 times 54 plus 99 times 11 plus 10 times 19 is the first element here, right?
Wait, but wouldn't it be like 10 times 3, then 38 times 254?
Yeah, it was, because transpose in this case, yeah.
Okay.
I was just saying, like, imagine the transpose wasn't there and this is only 4 elements long. But,
Oh, okay,
you are
gotcha.
correct. You are correct. Yeah, I just didn't want to transpose in my head because it was like I can't think about it in the moment, so I said like ignore that for now. But yeah, you're actually right about that. It's a transpose. So yeah, basically you take the first row, or the first row times the first column is the first element, like is now next the outputs first row first column value.
I see.
And then the second row of the second row times first column is second row first column in the next one. And then third row first column, fourth row fourth column. And let's say that this had more than 2 columns. You could do first row second column is now first row second column here, right? Basically, you multiply rows by columns over and over again, and add the linear combinations.
Gotcha. That makes sense now. For the transpose, are you like rotating it like 90 degrees, or how does it
You're
work?
like, so like, you know, like the main diagonal of a matrix is like from the top left to the bottom right.
Yeah.
Basically, it's like reflecting it over that line.
Oh, okay.
It's kind of hard to visualize, but like maybe you can look it up maybe quick.
Yeah.
But there's probably a matrix transpose thing out there, but it basically flips it over the main diagonal. If it's a square matrix, so if it's like a n by n matrix, it's pretty easy to do because it's just like a 1-to-1 correspondence, I guess.
You can also think
Oh,
of it as the rows becoming columns and the columns becoming rows, if that helps.
Gotcha. Yeah, I'm sure I can look that up. Wait, so I'm trying to like grasp the intuitive meaning, but it's like, say we're not looking at the transpose thing anymore, but so the 8 is looking at like the first pixel of the entire image and saying we want to weight it this much, in terms of like how much of it is as like, I think the first one was like cat, right? And then like the corresponding other 4 values associated, like the first pixel is saying like how much it is a dog, how much it is a whatever other animal. Is that right?
Yeah, that's how you could think about it. Yeah. They can also kind of think about like tracking certain features in a cat. I don't know, like we talked about this earlier, but like maybe like in general, cats have like whiskers. So like maybe that's tracking whiskers or something. And so it's saying like you found whiskers here in this on these pixels or something. And so that could be a weights in that case. Or like you said, it could be like, this is how much of a dog we think it is. This is we think of a cat it is in the first pixel. Generally, it's kind of hard to think of like I guess, pixel by pixel, because thinking about it holistically, if you looked at one pixel of an image, you can't tell if it's a cat or a dog or a fish. It's just one pixel.
Sure. Yeah.
But it is a lot easier to think about it like that, because then you can kind of think about the values of your weights and stuff, and like what they really mean. But there isn't like a really a one-to-one correspondence, more like a general correspondence of like these, like maybe like these certain rows correspond to certain things, but like not like a one-to-one, like element to element, I would say. But
I see.
Sorry, go ahead.
No, because it almost kind of seems like if you throw it like a random ass image, like completely unrelated to like animals, it'll like try to guess or classify it as something else.
yeah, that's actually pretty cool, because there's actually a lot of neural networks out there right now that basically you can train it to modify a certain image so that, like, let's say you have this picture of a cat on the left, right? The computer sees a bunch of pixels, right? And like a bunch of pixel values. And so you could have a computer like add noise to the pixel values, like add numbers to the pixel values, so that to every human looks pretty similar, but to the computer, it could be super different, and classify it really wrong. A lot of cool examples of this basically, but
There's a workshop on this in Advanced++.
oh, that's cool.
Yeah, I think it was recent. You can watch it. It doesn't, like, all the workshops for Advanced++ are independent. Like they're not connected. They're like one-offs, all of them. So you could just like look that up on YouTube and like watch that if you want, if you're interested in that.
I'll send you a link, but those types of attacks where you try to modify an image in a way that's not perceivable to the human eye are called adversarial attacks. And it's really interesting if you want to look into it. Also, regarding what Nikhil was saying earlier with looking at it pixel by pixel, it doesn't give us a lot of interpretability where we like, it's hard to determine why our model classified something as a cat when it did, just using simple logistic regression. But if you attend our advanced track workshop on convolutional neural networks, there's a more robust way to look for certain features where essentially we use something called a filter. And each filter in that neural network is looking for certain features in our image. And that way it makes a little more sense on why our network's able to classify the way it is. If that makes sense.
I forgot to stop recording.